Hey everyone, welcome to our channel. Today we're diving into something super exciting, a paper titled AlphaGeometry, an Olympiad-level AI system for geometry. It's a groundbreaking piece of work by Trio Tring, Yuhai Wu, Kwok-Vi Lei, He, and Thang Luang. These brilliant minds hail from Google Deepmind and New York University. Just imagine, a system smart enough to tackle Olympiad-level geometry problems. Now that's something. Stay tuned as we explore this incredible innovation in AI. You're not going to want to miss this. So, we've just uncovered the tip of the iceberg with AlphaGeometry. Now, let's dive deeper into why this research is a game changer. Picture this. Mathematical Olympiads, a real brain bender, right? These competitions are the ultimate test of logical reasoning. But here's a twist. Geometry, a significant part of these Olympiads, has always been a tough nut to crack. Why? Two main hurdles. First, it demands a level of math expertise that's just out of reach for most AI systems. And second, there's this big issue of scarce training data, which really puts the brakes on learning methods. This is why geometry theorem proving is kind of trailing behind in the neural network revolution, still depending heavily on human input. But, hold on. The real kicker in this paper? They're tackling this head-on, aiming to develop an automated geometry theorem prover. And not just any prover, one that can outsmart human Olympiad-level reasoning without needing to translate everything into formal languages or rely on existing human-generated data. Mind-blowing, isn't it? Let's see how they're planning to pull off this feat. Now, let's zoom in on some dazzling highlights of AlphaGeometry that are sure to knock your socks off. Picture this. For the first time ever, an AI system has outpaced the average human contestant in IMO geometry. How? By cleverly bypassing the need for human demonstrations. It's like building a mountain of knowledge with over 100 million synthetic geometry theorems and proofs. And get this, it's teaching itself to construct auxiliary points, which is a big deal in geometry, and it's doing it unsupervised. Talk about a self-learning powerhouse. But wait, there's more. This system isn't just playing catch-up. It's leading the pack, outperforming the latest and greatest on a grueling 30-problem IMO benchmark. And here's the cherry on top. It's not just solving problems, it's unearthing broader truths, like uncovering a more general theorem than the one from IMO 2004. It's like a detective, tracing back its proofs to spot any unnecessary assumptions. And the best part? This isn't just a one-trick pony. The approach they've developed has potential applications in other areas of theorem proving that are also starved for data. We're talking about a groundbreaking framework that could revolutionize how we approach data-scarce domains. Stay tuned, because this is just the beginning of a thrilling journey into the world of AI-driven theorem proving. As we glide further into the depths of AlphaGeometry, we stumble upon a milestone that's nothing short of astounding. Imagine an AI not just competing in the cutthroat world of International Mathematical Olympiads, IMO geometry, but actually excelling at it. We're talking about an AI that's cracked 25 out of 30 problems on the IMO benchmark. Just let that sink in. That's approaching the average score of the creme de la creme, the gold medalists. And here's the real showstopper. AlphaGeometry is the first of its kind to leapfrog over average human performance, improving classical Euclidean geometry theorems, those notoriously challenging puzzles from the IMO competitions. Even with the constraints of narrowly translated problems, this feat is nothing short of spectacular. It's like watching an underdog rise to the challenge and conquer a mountain that has long been the benchmark for the brightest reasoning minds. This isn't just about solving complex geometry problems. It's about redefining the limits of what AI can achieve in areas once thought to be the exclusive domain of human intellect. So, buckle up, folks, because we're witnessing a new chapter in the saga of AI and human ingenuity. Navigating through the labyrinth of AI theorem proving, it's crucial to spotlight the pitfalls of the paths already trodden. When we peek behind the curtain of existing methods, we uncover some real head-scratchers. First up, computer algebra methods. Sure, they've got the brains to theoretically decide geometry theorems, but there's a catch. They're like mysterious black boxes, lacking in interpretability. Plus, they can get bogged down in computational quagmires, with time complexity skyrocketing exponentially. Then, we've got heuristic search methods, those clever techniques using deduction rules and human expertise. They sound great on paper, but here's the rub. They're shackled by hand-coded templates. It's like trying to paint a masterpiece, but you're only allowed to use a handful of colors. And finally, the biggie. Translating these complex problems into general languages. This task is so Herculean, it's practically a field in itself. It requires a depth of math expertise that's not just a stone's throw away from the realm of developing reasoning methods. This translation conundrum leads to a severe drought in geometry training data, leaving AI systems parched for information. So, as we continue our journey with AlphaGeometry, it's these hurdles that make its achievements all the more extraordinary. It's not just about solving problems. It's about navigating a minefield of limitations that have long hampered progress in this field. Stay tuned as we delve deeper into how AlphaGeometry aims to rewrite the rulebook. As we waltz further into the world of AlphaGeometry, let's cast a glance at its peers and predecessors in the realm of AI-driven theorem proving. It's like stepping into a gallery of innovative approaches, each with its own flair. On one wall, we have the learning-based methods, those diligent students of human proofs translated into formal languages, relying heavily on human-curated demonstrations. It's like they're learning to dance by watching others, step by step. But AlphaGeometry dances to a different tune. Instead of following in the footsteps of human-provided proofs, it's composing its own symphony, generating synthetic theorems and proofs. It's like a composer who creates new melodies rather than just playing cover songs. No need for human translations. It's a trailblazer in its own right. On the adjacent wall, we find the search methods, equipped with reasoning engines and human-designed construction templates. Picture a builder using a set of predefined blueprints. Yet again, AlphaGeometry breaks the mold. It learns constructions from the ground up, building its own blueprint as it goes along. No reliance on human templates here. It's all about original design. So, as we delve into the intricate tapestry of related works, it becomes clear that AlphaGeometry isn't just another face in the crowd. It's rewriting the rules, taking a path less traveled, and in doing so, it's paving the way for a new era in automated theorem proving. The adventure continues, and we're just getting to the good part. Diving deeper into the magic of AlphaGeometry, let's unravel the mystery of how this AI maestro solves complex geometry problems. It's like watching a master detective at work, piecing together clues to crack a case. The process begins with the symbolic deduction engine, meticulously exhausting all deductions from the given premises, like a puzzle enthusiast combing through every piece. But here's where it gets really interesting. If the proof remains elusive, enter the language model, the AI's imaginative sidekick, proposing auxiliary constructions, those extra pieces of the puzzle that might just complete the picture. This collaboration grows the proof state, setting the stage for the deduction engine to take another crack at finding the solution. It's a dynamic duo, each playing off the other's strengths. This loop continues, a dance of trial and error, until eureka, the solution is found. For simple problems, a single construction might do the trick. But for the brainbusters, like the notorious IMO 2015 Problem 3, it takes a trio of constructions to reach the finish line. The beauty of this process? It's not just a black box spitting out answers. The proof steps are laid out, interleaved between neural constructions and symbolic deductions, painting a clear, step-by-step picture of the solving process. It's like watching a magician reveal their tricks, making the complex art of problem-solving transparent and interpretable. Stick around as we delve even deeper into the inner workings of AlphaGeometry and its groundbreaking approach to conquering Olympiad-level geometry. Now, let's take a stroll through the intricate labyrinth of AlphaGeometry's problem-solving process. It's like watching a maestro conduct an orchestra, each movement precise and purposeful. The symphony begins with sampling random premises, using a blend of deductive and algebraic reasoning to conjure up synthetic theorems and proofs. Think of it as the AI's brainstorming session. Next, like a detective poring over clues, it identifies the dependency difference via traceback, extracting those crucial auxiliary constructions. This is where the language model, pre-trained on synthetic proofs, enters the spotlight, fine-tuned like an instrument to focus on proposing these essential constructions. Then the stage is set with a new problem statement. This is where the real magic happens. The process loops until the proof is found. The symbolic engine steps in, expanding the proof state with deductive reasoning. If the proof remains hidden, the language model performs a beam search, like a spotlight scanning the darkness, proposing constructions to illuminate the path forward. These constructions are added, expanding the proof state, and the loop returns to the beginning, a relentless pursuit of the solution. And when the proof is finally unearthed, it's not just hastily presented. It undergoes a meticulous post-processing to extract the most streamlined, minimal proof possible. The outcome? A magnificent blend of the raw power of neural constructions with the safe, logical rigor of deductive engines. The result isn't just a solution, it's a human-interpretable proof, with every step validated, laid out like a story for all to understand. AlphaGeometry doesn't just solve problems, it narrates the journey of discovery, inviting us all to marvel at the elegance of its logic. Stay with us as we continue to explore the fascinating world of AI-driven theorem proving. As we peel back another layer of AlphaGeometry, we find ourselves gazing at the cornerstone of its brilliance, synthetic data generation. It's like stepping into a futuristic lab where AI concocts its own challenges. Picture this. At the heart of it all is a process that's both meticulous and ingenious. The journey begins with sampling random theorem premises. Think of it as planting the seeds of mathematical puzzles. Then comes the symbolic deduction, a methodical process where proofs are meticulously crafted, like a sculptor chiseling away at marble. Next, a technique akin to detective work, traceback, which extracts the minimal premises, ensuring that every step in the proof is essential, no fluff, no filler. And here's where it gets really clever. By identifying the dependency difference, it pinpoints those elusive auxiliary points, the hidden keys to unlocking complex theorems. It's like finding a secret passage in a maze. But wait, there's more. This isn't just a few experiments in a lab. We're talking about generating 100 million unique theorems and proofs, a veritable ocean of data. With traceback, it finds the most minimal elegant proofs. And in the midst of this, the language model is quietly learning, absorbing the art of crafting those all-important auxiliary constructions. So AlphaGeometry isn't just solving problems, it's creating them and then solving them in the most efficient, elegant way possible. It's a self-sustaining ecosystem of theorem proving, a virtuous cycle of challenge and discovery. Buckle up as we continue to dive into the fascinating world of this groundbreaking AI system. As we venture further into the realm of AlphaGeometry, let's bask in the glow of its achievements on the IMO benchmark. Imagine an Olympic high jumper effortlessly clearing bar after bar. That's AlphaGeometry for you in the world of complex geometry problems. It's not just competing, it's setting a new standard, solving a jaw-dropping 25 out of 30 problems on the benchmark. It's like watching a grandmaster chess player in action, moving pieces with precision and foresight. But it's not just about the quantity of problems solved. The quality is just as mesmerizing. The solutions AlphaGeometry comes up with aren't just correct, they're works of art in the world of mathematics, showcasing remarkable ingenuity. It's like a poet weaving words into verses that resonate and inspire. And here's the real clincher. When compared to human expert assessments from 2000 and 2015, AlphaGeometry matches up. It's like a new prodigy has entered the scene, mirroring the insight and depth of seasoned experts. As we gaze upon the graph illustrating its performance on the IMO benchmark, it's clear that we're not just witnessing an advancement in AI, we're seeing a new frontier in problem-solving prowess. AlphaGeometry isn't just a system, it's a trailblazer, reshaping our understanding of what AI can achieve in the realm of mathematical reasoning. Stay tuned as we explore more of this fascinating journey into the world of AI-driven theorem proving. As we delve deeper into the odyssey of AlphaGeometry, let's turn our attention to the fascinating world of ablation studies. Picture a scientist in a lab, tweaking variables to test the robustness of their creation. That's exactly what's happening here with AlphaGeometry. It's like testing the endurance of a marathon runner in different conditions. And guess what? AlphaGeometry is proving to be a real heavyweight champion, even when the training conditions are turned upside down. When the training data was cut down to just 20%, like running with weights tied to its ankles, it still managed to solve an impressive 21 out of 30 problems. It's like a mathematician working with one hand tied behind their back and still acing the test. But that's not all. When the beam search space was reduced by a staggering 64 times, akin to solving puzzles with a significantly narrower spotlight, AlphaGeometry still cracked 21 problems. It's demonstrating resilience and adaptability that's nothing short of remarkable. And here's the icing on the cake. When faced with an even larger challenge, a gigantic 231 problem benchmark, AlphaGeometry still delivered top-notch performance. It's not just surviving these tests, it's thriving, proving that it's not just about having all the resources, but about how effectively you can use what you've got. So, as we continue this journey, it's becoming crystal clear that AlphaGeometry is not just a one-trick pony. It's a versatile, resilient system, capable of adapting and excelling even when the going gets tough. Stick around as we uncover more about this extraordinary AI system's capabilities in theorem proving. As we continue our exploration of AlphaGeometry, we're about to uncover something truly spellbinding: the discovery of generalizations. Think of it as a mathematician not just solving problems, but also uncovering deeper, more universal truths. It's like a treasure hunter not only finding the treasure, but also discovering a new map to even greater riches. Take a look at this. By using proof traceback, AlphaGeometry is like a skilled detective, able to spot extra, unnecessary premises in problems. It's akin to a sculptor chipping away at marble to reveal the statue within. For instance, consider the generalized version of the IMO 2004 theorem it discovered. In the original problem, point O had to be the midpoint, and P was required to be between B and C. But AlphaGeometry threw out the rulebook and found that O doesn't have to be the midpoint, and there's no need for P to be snug between B and C. It's like rewriting the rules of the puzzle and finding a solution that's more flexible, more encompassing. This isn't just solving a problem, it's expanding our understanding of it, identifying an unused premise in the translated statement of IMO 2004, and unveiling a more generalized version that still holds water. This is a key capability for conceiving new mathematical ideas, pushing the boundaries of what we thought was possible. So, as we journey through the realms of AlphaGeometry, we're not just witnessing problem solving. We're witnessing the birth of new mathematical ideas, a testament to the power and potential of AI in the world of theorem proving. Stay tuned, as there's more to this adventure than meets the eye. As we reach the final slide of our AlphaGeometry journey, let's ponder not just on what has been achieved, but also on the exciting paths that lie ahead. It's like standing at the peak of one mountain and eyeing the next challenge on the horizon. So far, AlphaGeometry has been nothing short of a trailblazer. It has established synthetic data as a powerhouse for automated reasoning, breaking free from the chains of reliance on human demonstrations. It has soared past the average human contestant in the challenging world of IMO geometry, like a high-flying eagle surpassing the mountains. And it's not just about solving complex problems, it's about demonstrating a whole new way of tackling Olympiads without human proofs. The framework it offers is a beacon of hope for theorem proving in areas starved for data. But the journey doesn't end here. The future beckons with tantalizing possibilities. The team behind AlphaGeometry isn't just resting on their laurels. They're setting their sights on refining their approach to mirror the full spectrum of human reasoning capabilities. It's like setting sail for uncharted waters in pursuit of new discoveries. They plan to expand their prowess to a broader range of mathematical domains, casting their net wider in the sea of knowledge. Another intriguing pursuit is to explore the correlation between proof length and difficulty, a quest that could unravel deeper insights into the nature of mathematical challenges. And the ultimate goal? To achieve a complete representation of geometry, a feat that would be akin to mapping the entire mathematical universe. So, as we wrap up this enlightening expedition into the world of AlphaGeometry, let's remember that this is not an end, but a beginning of a new chapter in the saga of AI and theorem proving, where the possibilities are as vast as the stars in the night sky. Thanks for joining us on this incredible adventure. The future of AI is bright and full of mysteries yet to be solved.